Good afternoon, everybody, and welcome to today's Cold Chain Connect webinar, brought to you by the Cold Chain Federation. My name is Tom Southall, and I'll be introducing today's guest in just a moment. But for those of you who are new to the network, the Cold Chain Federation is the voice of the UK's temperature-controlled logistics sector. So we represent businesses across the cold chain industry to provide a united voice to government, to provide support on technical issues and networking, and also for events like this one. And the Connect is our regular, often weekly, sometimes bi-weekly series where we have a special guest to talk about a particular topic. And often our webinars focus on elements relating to cold storage and often to refrigerated transport. And today's session is very much in the latter category. We're looking at all things transport refrigeration, and really timely too, ahead of our Cold Chain Climate and Energy Summit next week, where transport decarbonisation is very much in focus. And today's guest, Michael Ayres from Flexible Power Systems, will be talking at that event too. So a really great introduction today ahead of that event next week. So thank you for joining us. Today's session, we're looking at all things TRUs with FPS, who are very much experts in the electrification of transport infrastructure. So Michael's got some really interesting slides to talk us through around comparisons around diesel and electric and building that business case. And I think Michael really taking a sort of situation report on where we are right now with electrification of transport refrigeration units and how kind of energy efficiency and grid connections and things like that all play into that business case. So great to have you with us. I'll hand over to you now to get going with today's presentation. Just a quick reminder, people can ask questions. We've got time at the end to put your questions to Michael, so please type those in as and when they come to you, and I'll make sure at the end that I put those to Michael. But for now, Michael, great to have you with us. Over to you for today's presentation.
Thanks very much, Tom. I will start the screen share. So good afternoon, everyone. I'm Michael Ayres from FPS. I'm going to talk a little bit today about decarbonisation options for transport refrigeration. Typically, there's a lot of focus in the sector on what's happening with van and truck fleets, usually less discussion of what can be done in terms of transport refrigeration. So firstly, a little bit about Flexible Power Systems. For some of you who may not be familiar with us yet, that we're a software company. We focus exclusively on decarbonisation of van, truck and transport refrigeration unit fleets, and our software can be used in sort of two time horizons. The first is when planning a pathway to net zero in, say, 2030 or 2035 and making investment decisions about how you should design your charging infrastructure, what vehicles to select, that kind of decision, and what order to work to your estate. And then the second dimension is in terms of real-time decision-making and optimization of electric vehicle fleets and charging infrastructure. Practically for our customers, that we do three flavors of things. Our principal product is our Operate platform, which is an enhanced charge point management system that is interconnected with vehicle telematics systems, logistics software systems, and it uses those connections in order to make sort of automated scheduling decisions about how to control vehicle and charger fleets in real time. Secondly, we have our TRU Fuel Saver proposition, which is about helping to overcome the barriers to plugging in transport refrigeration units in distribution center environments to unlock fuel savings associated with that activity. And then thirdly, we have our transition planning offer, which is about building a pathway to net zero over a multi-year time horizon. So, as I said, that a lot of the time that we're talking about sort of the truck decarbonisation or van decarbonisation, and often that sort of transport refrigeration units come as something of an afterthought. But there's a few different reasons why transport refrigeration unit fuel use matters. Firstly, that they're a quite significant proportion of the fuel bill. So if you can reduce TRU fuel consumption, then you can reduce your operating costs. Secondly, they're a significant part of the Scope 1 emissions story, and so we can't get to net zero without decarbonising transport refrigeration units. And then thirdly, that transport refrigeration units have been shown to have a disproportionate impact on local air quality, which means there's implications for both sort of staff wellness and distribution centre environments, and for the communities in which that we operate. So if we're looking at alternatives to our incumbent technology, diesel, that there's a few that we're aware of that are in development at the moment. So that sort of working round the clock, that you've got hydrogen fuel cell technology, which is sort of being piloted by some OEMs and fleets at the moment. There's cryogenic technology, which I've historically been involved in development of sort of challenger organisations like sort of Dearman, and then sort of innovations like sort of Polar Stream have been sort of in the marketplace for a number of years. And then you also have biofuels, which are an option for sort of running conventional diesel systems, and then also electric transport refrigeration units, where I think a lot of the growth and development has been over the last sort of 5 to 7 years. So we'll start by sort of thinking about how these technologies compare, but from a sort of thematic perspective. And for sure that there are very many sort of metrics that you could use to evaluate them, but I've started with a few simple ones. So in terms of the capacity to deliver fuel cost savings, that really of all of those different options, that electricity is the most likely to be able to deliver fuel cost savings. That's because the production efficiency of hydrogen cryogenics is generally sort of too low to be able to be substantially cheaper than diesel, and that biofuels generally carry a cost premium, which is potentially likely to increase over time. All of those technologies are capable of addressing Scope 1 emissions, and also can be a sort of really useful part of the journey to net zero for fleets. All of the technologies on that list also address air quality, though with biofuels it's slightly more of a grey area because there's some sort of nuance to that position. You see real differential between the technologies in terms of capital investments, that hydrogen is probably the least competitive at the moment and is likely to remain so. That is to do with the sort of increased costs of hydrogen containment and storage, because you require high pressure vessels, and also the high costs of hydrogen fuel cell technology, because it's typically produced in very low volumes and has a sort of relatively high complexity compared to some of the other technologies considered there. Cryogenics and electricity are sort of somewhere between sort of where hydrogen is and diesel technology in terms of cost premium, and that's principally driven by sort of volume. And then you have biofuels, which potentially could have sort of almost no equipment change in order to sort of make them feasible. It's probably worth flagging sort of the reason why that we can't sort of simply adopt biofuels at this time, which is to do with the sort of availability of feedstock. For sure, it's possible to get HVO and HVO in significant quantities, or sort of biomethane, such that you can perhaps decarbonize an individual fleets. And many fleets are using this fuel at the moment as a sort of really valuable part of their transition. And it sort of bridges a gap in the short term, whilst the sort of other technologies on that list are in sort of the development phase. However, that there's insufficient biofuel feedstock to enable us to completely decarbonize any of the commercial vehicle fleets that we operate in the UK, and so that they can only ever really be transition technology. So one of the questions that we get quite frequently is whether the electric transport refrigeration units can be cost effective, given that we believe this to be the sort of most likely long-term solution to sort of decarbonising transport refrigeration. And the answer to that is that it depends. It depends on sort of how efficient those TRUs are. It depends on sort of what you assume about fuel costs. Depends on sort of how expensive that you think they are to purchase, the duty cycles you're doing, and even sort of factors like the weather. But what I thought I would do today is sort of share some economics as we understand them, that because it's useful to put numbers around a situation like this. And I think that we can show you some of the dynamics that we see when we're looking at deploying sort of electric transport refrigeration units. As ever with transport refrigeration, many of the numbers are in debate, so we'd certainly be interested to hear from anyone who thinks that the numbers are different to the ones that I'm about to show you. So I'll start by sort of giving you an indication of the technology assumptions that we've used for this analysis. So we've got sort of capital costs for sort of purchase of single and multi-temp fridges. We have fuel costs on a pound per litre and pound per kilowatt hour basis. These slides were made prior to the start of the conflict in Iran, and so may be adjusted as a result of those over the coming months. And then there are also sort of carbon intensity factors for the two fuels that we're considering. We consider it likely that there will be a price premium between sort of single temp and multi-temp configurations of technologies that we're looking at, and that's why we have sort of two different sort of sets of scenarios there. The next thing that you need to know if you're about to compare the sort of economics of electric refrigeration with diesel refrigeration is how much fuel the transport refrigeration unit is likely to use. And the answer is that it depends as well. It will depend on the transport refrigeration unit, that there's dramatic differences between sort of models and brands, and also the age of the transport refrigeration unit will make a difference. There are differences in terms of insulation, set points, operating bands that you set the fridges to, the duty cycle that you put them on in terms of whether you've got sort of set points for frozen or chilled, how many door openings that you have, the length of those duty cycles, and also the weather can affect that. As a useful sort of start point for this type of analysis, that there's a sort of generic duty cycle that was developed by the sort of ZEMO partnerships to try and sort of quantify the sort of fuel consumption and emissions impacts of transport refrigeration units a few years ago. I can give you an overview of the sort of cycle. It's highly simplified compared to the sort of multi-drop operations that some of you may be undertaking, but it's useful in order to be able to sort of drive a comparison. So the testing took place at 15 degrees C ambient temperature. The duty cycle started with a pull down, which took varying times depending on the set point that was trying to be achieved and the fridges. And then a consistent 3 hours of temperature maintenance, a half-hour door opening, and then a recovery. Through this analysis, we've tracked sort of frozen and chilled results, as well as multi-temperature results, so you can see the sort of comparison between them. So each one of those individual duty cycles used a different amount of fuel. I imagine, as many of you would expect, that the sort of least fuel was used for the chilled duty cycle, intermediate amount was used for frozen, and then sort of the multi-temperature configuration actually used more fuel in this set of testing. The other feature you'll notice of the fuel usage profiles that you can see here is actually that sort of the chilled, the most sort of energy intensive part of the duty cycle is around sort of ongoing temperature maintenance over an extended period. Whereas that sort of when you look at frozen operation, that the sort of the pull down process is much more energy intensive, and that has implications for where that energy consumption is likely to take place. Now, few, if any, operators do just one shift per year, and so that you need a mechanism of understanding sort of how those individual test results may sort of translate into sort of years worth of fuel consumption. So what we've done is looked at sort of a model of sort of the number of shifts like that you might complete across the week, and sort of use that as a driver for our sensitivity analysis, going from sort of doing 5 shifts per week, which would be sort of 5-day-a-week operation, single shift, all the way through to sort of 7 days a week, triple shifting the fridges. And you can see in this chart here what the distribution is of sort of implied annual fuel consumption. At the very bottom, that it's sort of 1,600 litres of diesel a year. The very top end, that you're sort of knocking on the door of 11,000 litres per year. Now, if you have got an idea of what your fuel use is, that you need to have a sort of view of what your likely sort of diesel consumption, what your likely electricity consumption would be to accompany that. So actually, it's relatively straightforward to perform this conversion. We know what the energy density of diesel is. We know the likely part load efficiency of a diesel engine. We know the likely mechanical efficiency of a sort of drive shaft. So we know probably how much of every sort of litre of diesel's potential is going into the sort of shaft of the vapor compression cycle to cool the fridge? And the answer is about sort of probably 2.4 kilowatt hours of that initial nearly 10 kilowatt hours that you have of energy. It's a little bit more complicated than that because there are differences between electric transport refrigeration units and sort of diesel units, so that it might be in terms of some motors for sort of braking energy recovery. It could also be sort of solar is an incredibly popular component in these systems. That if you look at on a sort of generic basis for a sort of 10% capacity factor, and you imagine that you can cover the entire roof of a sort of trailer with solar panels, you can get some sort of quite impressive quantities of energy generated by solar panels. You can see, for example, with a single shift field operation, it's 160% of the total required energy. For the more energy intensive cycles, that you'd end up sort of around about half or sort of a quarter. In the real world, that the results will be sort of less attractive than this, and that's because that the solar panels tend to be sort of not optimally arranged in terms of angle to capture the maximum sunlight. They also, solar generation may not always coincide with when the energy is required for the trailers. There may be a misalignment between duty cycle and operating times, for example. And so we've assumed for the purposes of this analysis that maybe an ETRU is sort of 30% better than that sort of diesel benchmark to account for these sort of various factors. So what that gives you, if you sort of put those factors that I've outlined all together, is a point at which you can achieve kind of TCO parity for an electric versus diesel fridge, so that you, if you're doing the sort of chilled only operation, when you look at a sort of 7-year lifetime for the asset, you probably need to be running that sort of about 13 times a week. If that you're running in frozen mode, it could be only 8 times a week. And for the sort of multi-temperature example here, it's sort of about 9 times a week. Because it's cheaper to run the electric fridge than it is the diesel fridge, obviously that the sort of TCO use case sort of favors higher levels of utilization. And then another way of looking at this is sort of what the paybacks would likely to be for the increased capital investment for the electric fridge in comparison to the diesel fridge. If we're looking at sort of single shift type operation, that this analysis would suggest that you're somewhere between sort of 8 and 13.5 years payback when you're doing single shift. Double shifting brings you down to sort of 4 to 7 years, and then if you can get sort of triple shift operation out of this equipment, then you get down to sort of 3 to 4 years payback, which begins to become sort of very interesting. So I guess the takeaways that I have from this are that ETRU economics are potentially pretty attractive, and actually attractive under sort of a range of different use cases, and that this is something which we think will only get better with time as the ETRU production begins to achieve scale economics, and so you get cheaper fridges with a smaller cost differential. The thing to note, though, is when we're sort of thinking about trying to achieve a sort of net zero target, is that even as these fridges become more competitive, that they will be part of a sort of multi-year fleet transition, which is something that we see in the sort of van and truck sector, where the fleets may take sort of 7 to 10 years to transition their fleets. And so there's a question about what happens in terms of emissions in the intervening period. The other thing which is worth mentioning is that all ETRUs will probably at some point need to be plugged in, and so that there's an infrastructure piece as well that needs to be considered. And often when you look at sort of van and truck deployments, that sort of one of the hardest bits to complete is actually the sort of infrastructure side from a sort of cost perspective. Now, it's a very different situation for transport refrigeration to vans or trucks, that diesel vans and trucks can make little to no use of electric vehicle charging infrastructure. However, that's not the case for diesel transport refrigeration units, because the standby mode enables these devices to be plugged in when they're in distribution center environments. It means that diesel transport refrigeration units can make use of the infrastructure that you require to support ETRUs in the long term. And actually, it's quite a good thing to do because it will reduce the fuel costs and carbon impact of your diesel transport refrigeration units whilst they're in depot environments. So to give you a sort of idea of what the economics look like for plugging in your diesel fleet whilst it's in a sort of distribution center environment, that based on the assumptions that we showed you at the front of about sort of 22 pence kilowatt hour for electricity and sort of £1.10 for diesel, and the efficiency that we showed you, that mains electricity is more than 55% cheaper than diesel per unit cooling delivered, and you get about an 83% reduction in carbon emissions. And that's a particularly interesting metric because some of the fleets we work with, that 2/3 of their fuel use happens whilst they're in distribution center environments. And so that there's an opportunity to sort of substantially reduce emissions and fuel costs without changing your equipment today. On the right, there's a sort of simple example about what the sort of typical 7 megawatt hours per year usage cycle looks like. It's about 3,000 litres of diesel saved, about £1,800 in net fuel savings, and about 6.2 tonnes of CO2 per year saved. And that's what we typically see per plug that we operate. But again, that its economics are sort of very tightly related to sort of how much that these assets are used. So you can see on the left a sort of annual fuel savings versus electricity consumption per plug. The light green shaded area is the range of uses that we see on sites that we manage across our estates. So typically from sort of about 5,500 kilowatt hours per year up to 11,500 per plug at some sites. And so that those plugs are yielding for operators between sort of about £1,600 and £3,000 a year in net fuel savings. Then in terms of how quickly that they pay back, because there's significant investment in them to be made in terms of both the plug itself and in terms of the civil works to support them, we typically see paybacks in the range of sort of 1.5 to 3 years, which is quite attractive. The carbon emissions savings which are associated with that level of fuel saving are quite significant too. That around about the sort of mid-range, you can see that the carbon savings are sort of broadly equivalent to what you might get from sort of substituting a diesel TRU for a chilled TRU, and then actually that sort of towards the upper end that you're achieving a sort of meaningful proportion of the total savings which are delivered by even a sort of more energy intensive frozen or sort of multi-temp fridge operating a sort of double shift 7-day-a-week pattern. So the reason that sort of these higher levels of energy consumption are possible is because actually that multiple vehicle assets can use a single plug, and so it gives you potential to deliver sort of a higher level of carbon savings per unit. Another way of sort of looking at the sort of relative economics of these sort of two systems is how much it costs in upfront capital investment to save a recurring ton of carbon dioxide per year. Infrastructure costs sort of between £400 and £800 per ton per year. And then the sort of at current prices, the sort of ETRUs cost about sort of 3,000 to 3,100 tons, so 3,000 to 3,100 pounds per ton of carbon mitigated per year. And so the takeaway from this isn't that you shouldn't do sort of ETRU fridges, but simply that the infrastructure to support them in the long run has an immediate payback now and an immediate impact in terms of your carbon emissions, that it will enable you to sort of move close to your net zero targets whilst ultimately working to that goal. So if that plugging in fridges is such a great idea, how come that not everybody is doing it already? And typically we see sort of 4 things that are sort of delaying this transition for some of our customers. First is around the sort of business case. So typically that the sort of standby infrastructure in distribution center environments is sort of very lightly monitored, if at all, which means that the fuel savings which are being delivered that I showed you from that sort of theoretical case on the slides aren't being tracked in real time, and that can be a problem if you're looking at the multi-year rollout of infrastructure where the finance departments are looking for evidence that the fuel savings that were promised at the initial project were actually delivered. So there's a lack of transparency in terms of usage doing that. Often that fleets have problems with compliance and driving usage. That this can be because the drivers don't understand what the value is they're plugging in. They don't understand that there are fuel and carbon savings associated with it, or they're not communicated to drivers. Similarly, the drivers in deployments we've been involved in have sort of expressed concerns about infrastructure reliability and not wanting to, for example, get out of a cab on a cold November evening if you think that the plug's infrastructure at the site is always broken, and so it'd be a wasted trip. And so that there's a link between sort of guaranteeing infrastructure uptime and communicating this to drivers and achieving sort of driver compliance. And then the other problem that we've seen in some locations is power constraints. When you look at very large sort of retailer type distribution centers that may have more than 200 bays on them, that you're actually into sort of multi-megawatts of power required to support sort of plug infrastructure for diesel and ETRUs, and not every distribution center can accommodate that. Which is why that we developed a sort of solution to this, which we call TRU Fuel Saver. There's two components to it. One is a sort of smart plug, the other is a management platform. The smart plug is a little different to the sort of plug infrastructure you might normally see in a distribution center environment. The principal differences to it are that it has an energy meter built into every single one of them, which gives you extremely granular information about sort of consumption at bay level. It also has an internet connection, which gives it sort of the ability to continuously stream this data, and a remote switching capability, which can be used for power management. It also has a couple of features like integrated RCDs and things like that, which are intended to, alongside constantly reporting status and heartbeat, improve the uptime of the device. The other side to this is the sort of management platform. It's more than just talking to these individual plugs. That the platform is coupled typically to yard management systems. That's a useful thing to do because it enables you to identify what vehicle is on what bay, which can help with compliance tracking, but also is very useful if you're going to make interventions with regard to load. So for example, you wouldn't want to turn an alternator fridge off, or perhaps you wouldn't want to turn off a sort of ETRU that was sort of partway through its charging cycle that was scheduled to go out shortly. We also track power usage at the site in order to decide whether to intervene in terms of undertaking load control and also weather. And doing all of that enables us to sort of continuously sort of report cost and emission savings, which can be used to support compliance and the forward business case, investing in the infrastructure. We issue alerts if any of the infrastructure goes down, so that there are no wasted trips to plugs that don't work, and that plugs which are broken can be fixed quickly so they can carry on saving fleets money. And then that we also have the ability to intervene from a sort of load control perspective, and also from a fault resolution perspective in these assets to keep them up, and also manage sort of scarce power availability at sites. This is what the system looks like, that there's kind of an element to it which has sort of reporting of sort of load control interventions, and another one which is to do with analytics at both sort of individual site level and also at the individual sort of site area level. There's a short little demo here that I can give you to sort of show you what the sort of implementation looks like. That these are the comparisons between sites, which can be used to sort of judge whether the sort of compliance is taking place. There's then at the individual site level the capacity to sort of drill in and see sort of whether the sort of specific warehouses on site are complying. There's then also, this is to do with the sort of power intervention, so you can see how often that the sort of interventions are being triggered in a given period to sort of minimize sort of power consumption at the site and avoid breaching sort of site load. Great. So that was a bit of a whistle-stop tour of the economics of transport refrigeration units on both the sort of vehicle and the infrastructure side. If you're interested in learning more about any of that, there are various guides which are available on our website, as well as information in relation to the TRU Fuel Saver product. My contact details are here. I'd be very happy to hear any questions that you have now, or see you at the Cold Chain Federation Sustainability Live.
Thank you, Michael. Really interesting presentation, and I know you recognise that there's a lot of variability that goes into TRU usage, but to actually see those numbers of a kind of average scenario and see cost savings and payback, especially in terms of how hard you sweat the asset, I found really, really interesting. So I think lots for people to kind of digest there. Couple of questions from me to kind of get started. I know you obviously were focusing on transport refrigeration today with the CCF's audience, but you also work in the HGV space. When you look at things like payback between eTRUs and diesel TRUs, how different is that have you looked at the numbers for electric HGVs as well? Because one of these things the CCF is always doing is sort of assessing policy on HGV decarbonisation and then looking at what that means or doesn't mean for eTRU. So really interested in whether you've done those comparisons and whether the business case is stronger, weaker, the same.
So with HGVs, the answer is a little bit like TRUs. It depends. It's very strongly linked to utilization. However, the sort of battery degradation is a sort of bigger issue in that marketplace. And range constraints are sort of more of a concern. Typically, we would see that eTRUs tend to have a sort of much more attractive business case than eHGVs and shorter paybacks. Particularly when you begin to consider the infrastructure side as well. So what often makes the business case quite difficult for sort of eHGVs is the charging infrastructure that's required to support very high utilization levels. So people end up investing in sort of 350 kilowatt DC rapid chargers that cost sort of 50 grand on top of the vehicle that may cost sort of 250, 300 grand as well. And because that charging infrastructure generally can't be used at sort of very high rates, it's very hard to generate a payback on it. Whereas the advantage that sort of eTRUs have is that their sort of diesel TRU cousins can make use of that electrical infrastructure and contribute to the overall payback of the sort of decarbonisation project. And so I think it's a unique opportunity that we have in that particular segment, I think.
Absolutely, yeah. And obviously the government there's a lot of funding available on the eHGV side and for charging and things like that, but not so much for TRUs, and possibly that because the business case isn't quite as strong for eHGVs. There are things like charging schemes for electric HGVs. Does that apply to if somebody was looking to get shore power hookups in their depots for their eTRUs? Is there any funding they can?
That's a good question that I've not considered, whether the mechanisms like the workplace charging scheme would apply to transport refrigeration units. But we should definitely ask the question. I think that the situation is nuanced with regard to sort of funding which is available for sort of the VHGVs, because there's obviously the sort of the plug-in vehicle grants and there was the recently sort of the depot charging scheme as well, which TRUs wouldn't have been able to qualify for.
Yeah, there was I obviously inquired to the DFT around that, and their answer was yes, but I think they misunderstood the question to some extent, which is what we come across quite a lot talking about TRUs. But kind of what I ascertained that was potentially you could use that funding if you actually did have an electric HGV already. That would sort of qualify you for maybe putting in chargers if those chargers were going to be TRUs, but it was a bit of a workaround. So yeah, often they're not designed. These schemes are not designed with TRUs in mind, but we're constantly kind of arguing the case to government that it's clearly transport infrastructure and it should be part of those schemes.
Yes, exactly. I suppose the thing that I would say contrary to that point is that actually the sort of the levels of funding which are available for particularly sort of like truck decarbonisation are very small compared to the scale of the problem. So it's sort of great to get a sort of pilot project, something like ZHID in terms of getting your first sort of few trucks, having that heavily subsidised, but it's not actually going to do anything about the sort of next 5 years of adoption, which are going to be quite tough, where there is this significant sort of capital cost increment. I think the thing which is different about the infrastructure for ETRUs, or simply plug infrastructure for sort of diesel TRUs, is that the business case is so strong for that it actually can kind of outcompete a lot of other energy efficiency initiatives that you might have in your estate. I mean, there's not that many sort of capital projects you can do in the energy space that are going to deliver you a sort of 1.5 year payback if you push the utilization really high, are there?
No, that's a good point. Yeah, and then in terms of, I guess, moving on to the shore power element, that area really fascinates me, because it seems quite an obvious one to kind of to reduce, obviously, diesel costs, but you mentioned the air quality and things like that as well. That always surprises me when we're visiting members there aren't more shore power isn't more shore power being utilised. You mentioned some of the challenges to that. How much of it is a kind of, I guess, a behavioural thing that people are used to running TIUs in certain way,
yeah.
which is using diesel as that kind of, well, it's on stand, we just turn that on. Are we trying to work out what that balance is between behavioural stuff, and then obviously there's that cost of installation of shore power. You've got to potentially reorganise your depot a little bit to have charging areas, and that again is a bit more behavioural. Yeah. Is there an element of that to it?
So I think that the root cause of it is when we had the red diesel duty exemption, which meant that the incentives were sort of pretty weak, and so it means that for decades that many fleets, because there's obviously many things to think about if you're sort of temperature controlled fleet who has a day job, have not been focused on this issue, and so that there hasn't been sort of a great deal of focus on compliance and things like that with it, and so that for many organisations, particularly like retailers and things like that we work with, that there are programs now to introduce this infrastructure, which requires quite a lot of behaviour change in order to make it work. And actually, it's sort of like with any kind of behaviour change project, it actually needs to be kind of reinforced periodically, so that we see, when we look at the sort of consumption of some of the sites that we manage, that you put the infrastructure in, you have a big sort of wave of training, that the consumption goes way up, that the economics look extremely attractive, and then actually have to go back probably every 12 months to kind of go and reinforce the training, reinforce the messages and things like that, in order to sort of achieve the sort of top levels of performance.
Yeah, absolutely. And you mentioned red diesel, which I think there was already innovation happening in the transport refrigeration space, but it absolutely kind of early 2020 sort of kick-started that a lot of the innovation we're seeing now, I think, because of that business case becoming stronger. And that was one of the arguments against for removing that subsidy, and that certainly seems to have kick-started a lot of the innovation that we're seeing. And largely now it is an industry-led journey, the decarbonisation of transport refrigeration. There's not a lot of government intervention at all. We don't have phase-out dates. We don't have restrictions we don't have anything. It's being driven by industry, which there are positives and negatives to that. Is there anything in your kind of work, especially when you're looking at depots and electrification, is there an area you think the government could do more to support refrigerated transport operators in the journey to electrification?
I think that it will. So I think that where the challenges will be around grid connection access, which is one of the things which is sort of major problem in the sort of the propulsion sort of technology space as well.
Yeah.
Because it's, in many cases, it isn't that the economics are so far away that the sort of massive subsidy is needed.
Yeah.
It's that barriers to actually sort of executing this need to be removed. Does that make sense?
Yeah, absolutely.
And that one of them will be around sort of connection access, inevitably, and that the interplay between sort of what's happening with transport refrigeration unit decarbonisation and what's happening with the sort of wider sort of transport arena. I think that they're pretty different things. That if you look at the sort of economics of buying a sort of 300 grand electric truck and installing charging infrastructure for it, that we're very far away, and you can see that sort of only the very largest operators is going to be able to do that without subsidy in the short term. Whereas that you look at some of these technologies, and that, you know, if you can get ETRUs into a sort of 3 to 5 year payback kind of horizon, or sort of fuel cost perspective, if you can get depot infrastructure down to 1.5 to 3 year arena without subsidy, that I think that the argument is about sort of spreading awareness and removing sort of operational barriers to doing that, rather than necessarily requiring sort of cash to make the economics more attractive.
Yeah, and I think it's obviously going to build as more and more people adopt EHTVs and ETRUs, but it sort of feels to me like the system can just about cope with the level of adoption at the moment. But if within 10, 15, 20 years, you're looking at a depot that might have 200 HGVs, 400 refrigerator trailers, and then maybe a cold store operation as well attached to it. I haven't seen a clear argument that says how the kind of grid will adapt to be able to support that. But yeah, hopefully it's coming. But
well, I think it. I mean, there's not there isn't a technical barrier to doing that. We don't have to invent anything to get enough power in for 200 HGVs. It's not like invention is on the critical path. There's a sort of a chicken and egg problem, really. So that the problem is that distribution and transmission network operators are not allowed to build capacity speculatively. So they can only do it if there is proven demand.
Yeah.
And so there's this kind of gap between sort of where the sort of fleets are at the moment and where the sort of network providers are at the moment, in terms of, and we need to bridge that by building some more certainty about what's going to happen. One part of that is to do with, I think, government, in terms of sort of making clear exactly what the rules of the game are, and so that everybody knows that, you know, we're sort of working towards this deadline to try and achieve this. The other part of it, I think, is to do with the industry cooperating to try and sort of express sort of what operators' intentions are, if that makes sense. So that, you know, if all of the operators in the region were able to communicate to the distribution network operator what their next 5 years worth of intentions were around electrification, that would be very helpful to the DNO in terms of planning for that.
Yeah, and I think that kind of, there have been some attempts between government and industry to try and predict the future energy demand and start to do that, but I think that it's found it challenging to build that. But
it's the problem is it depends, doesn't it? But,
yeah, exactly. But I think we could talk about this for hours, but we're just about out of time, Michael. But as I mentioned at the start, we are back with our Climate and Energy Summit next week. So if you want to meet Michael in person and hear more from him on our panel to do with transport decarbonisation, then really recommend, if you haven't already, you sign up for the Climate Energy Summit. Bookings are still open, but they close this Friday, and we're nearly at capacity. So you can scan the QR code there or go on the website to register. Thank you, Michael, for all that insight. Loads of really great stuff, and really recommend that people get in touch with you to discuss their own requirements. And I'll see you next week at the summit, and hopefully see everyone else there too. But until then, we'll wish you a good afternoon.
Okay, thanks very much.